So, good morning, and we will look at a new topic for the next 2 or 3 classes. So, this will be on electrokinetics. Okay. So, generally I mean when we talk about microscale phenomena, although this is not part of heat transfer, but generally a very important aspect of microscale flow is how to manipulate some of the forces at that small scale and make use of those forces to drive the flow. Okay. So, this is a very interesting topic, and therefore, without mentioning this, I do not think I will complete micro nanoscale part. So, I think when you now deal with microscale phenomena, as you have seen, especially apart from the gas flows, when you talking about the liquids, there is really not so far whatever we have seen with the single phase liquid flows through micro channels. In terms of hydrodynamics or heat transfer, there is nothing much very new that you have that you have to learn to understand microscale phenomena, because most of the correlations are equally valid for macro channels, and specifically we are highlighting certain important features such as the surface roughness and so on, which becomes important, but they can also be considered for macro channel case. So, in that sense, if you have a course where only micro scale part is covered, you may feel or you may underestimate the content and also the physics. Okay, you might think there is nothing really interesting or new to learn in the micro and nano scale, and it is all just re-emphasis of the macro scale phenomena with some alterations. Okay. So, that portrays a very simplistic kind of a picture, and in fact, also to say hydrodynamically, most of the micro scale flows are in the laminar regime. So, that makes it for a average fluid mechanics background person, makes it far more easier to deal and understand than with the macro channels. With the macro channels, you talk about separately laminar, turbulent, and you give a lot of emphasis to turbulent flows, because most of the engineering problems are of turbulent nature, and therefore, you put so much of struggle to do experiments and modeling simulations of turbulence, whereas in the micro channel everything appears to be laminar and pretty straightforward. So, you use the same continuum equations, only that you call this as micro with a fancy name, and you are still using the no slip boundary conditions. So, everything seems to be much easier, only that it is the keywords are far more captivating than in the macro case, but that is why I started with the nano scale transport. Okay. So, if you want to really build a bottoms up approach, you have to understand that there is a rigorous physics and theory at the nanoscale level. Okay. Yeah. So, when you are building like this, you understand the foundation is actually quite strong. You talk about the atomistic scale, energy carrier level approach. So, that is the foundation, and that can be applied through all the regimes, but the micro scale, however, is a little bit fuzzy patch. Okay. There is no separate theory for micro scale. So, either it has to be a bottoms up approach or a top down approach. So, some micro scale, what happens is it is difficult to build a bottoms up approach, because it is neither really nano nor macro. So, we resort to the top down approach. We still use the continuum equations and everything, and we only focus on certain flow physics, which are more relevant when your channel dimensions become smaller. But in terms of the mathematics or rigor, it is not very difficult. Okay. Whereas, the nanoscale you cannot do a top down approach, it will fail. Okay. You are really talking about subcontinuum, and therefore, we are building a completely new theory, fundamental perspective, from fundamental perspective. We do not assume anything, right, no continuum, nothing. So, we just start from the building blocks and we build it, and the same approach can be extended to micro scale. However, it is not worth doing such a very rigorous approach. Computationally, it is very expensive to solve Boltzmann equation for say liquid flow in microchannel, when most of the flow physics can be explained by continuum equations. So, it is far easier to solve the Navier-Stokes equation than solving Boltzmann transport. Okay. So, therefore, any subject on related to microscale, unless you have a foundational understanding of nanoscale, will not look complete, and also will make you feel that it is a very trivial course, correct. So, most of the correlations are equally valid, macro and micro. Only for the gas flows you have the problem of Knudsen numbers exceeding 0.1, and therefore, you bring in all the slip boundary conditions, but for liquid flows there is absolutely no problem. So, now therefore, people working in this field somehow have had the privilege for some time to get away with using simpler equations, but trying to understand new phenomena at that small scales. Okay. So, electrokinetics is for example one of them. So, this is not a topic only related to microscale, this can be there even for any surface or any length scale, but this becomes more important, these forces become more important when the channel dimensions become smaller, and therefore, you can significantly use this force to cause a motion. Okay. And therefore, we talk about electrokinetics particularly in microscale transport. The same physics and same theory holds equally well for any scale. Okay. But as we said that we still stick to the same equations, but we emphasize only the important physical phenomena occurring at the small scales. So, electrokinetics is one such phenomena. Okay. So, what is so relevant about electrokinetics? The electrokinetics has become a very important buzzword of microscale flows, because the entire domain of microfluidics is nothing but microflows with electrokinetics, so and other different kinds of kinetics which are brought in by external forces or forces which become very important at small scales, surface based forces. Okay. So, this has brought about a completely new subject called microfluidics, and microfluidics has become very important due to many applications in small scales. Electronic cooling could be one of them, but more than that, microfluidics has spread into biological and medical applications. Okay. And that is where it has gained immense popularity, and so a lot of people from biology and medical field, since they do not have a good knowledge of fluid mechanics, so they want to however build devices which are of small scales, where they can process, synthesize, separate for example DNA. So, that is one application, separating platelets from plasma in the blood. Okay. This is done very regularly. Sorting of blood, you count the kind of platelets. Okay. How do you count how many RBCs are there, WBCs are there, So, there are some sorting and counting mechanisms which are conventional and which are expensive, which takes time. So, the idea is to build what is called as a lab on a chip device, that is a portable handheld microfluidic device, where you put some sample of your say blood, and this microfluidic device uses these electrokinetic or another kinetic principles, and it will kind of say separate the plasma from the platelets, and you will at the end of this small device you will be able to count how much is the platelet count in your blood. So, it is a handheld, you do not even have to go to a laboratory and use the expensive equipment. So, such kind of very compact portable biomedical applications are all emerging now. So, even many companies including our Apollo Pharmacy, they are actively engaged in manufacturing such handheld lab on chip devices. So, that is how microfluidics has gained immense popularity. Okay. So, it is essentially that you apply these physical phenomena, these scales to put into use for medical applications, where it has become necessity to make the devices, diagnostic devices, testing devices as small as possible, so that everybody can buy it at a cheap price and they can just use it on their own. Right. One example is how do you test for diabetes. Okay. So, some 10-15 years back, all the time you had to go to the hospital, okay, where they prick your finger and then they test it. So, now you have portable glucose testing machines, so you just it is a small strip, you pick it, you put it, and immediately it will give you the digital value. That is a very good example of a microfluidic device. Okay. So, inside it is nothing but a lab on chip device which will analyze the blood sugar level in your blood, and immediately it senses what is the value. Okay. So, there could also be some chemical reactions that you can induce within the small microfluidic device. Okay. Some chemical has to mix with the blood, some reaction should happen, and you should find that the chemical compound is converted into this much percentage of this. So, therefore, this is correlated to your amount of blood sugar. So, all these are usually built on such kind of principles. Okay. So, therefore, most of the key microfluidic functions require various lab on chip devices, and what kind of principles they use, whatever we know, pumping, but pumping cannot be now done like you are putting a conventional big pump. It has to be done in such a way that you pump microliters, very small volumes of fluid, and you have to also make sure that you do not have an external mechanical pumping device. So, it can be integrated within the same lab on chip device such a way that it uses the forces at the small scale to pump. So, we have to therefore find ways to build a pump which is based on such kind of phenomena. So, therefore, pumping, mixing, okay, thermal cycling, dispensing and separating. So, mixing is another very important aspect in microfluidics, because most of the times, as I said, the regime is laminar, and therefore, the mixing is not so great, right. So, turbulence is always very good for mixing. So, in conventional case, in heat exchangers, so if you want to mix two fluids, you make them turbulent, you mix them and you do not have any problem. So, the turbulent diffusion is quite high, whereas if you are talking about the micro channels where it is laminar, so it is very difficult to achieve mixing, and therefore, we have to find out alternate ways of promoting this mixing process. Separations. So, you have to also find out ways to separate two different components of the fluid. For example, if you take blood, you want to separate the plasma out, platelets out. So, how do you devise? So, you can have a channel which is bifurcating. Okay. So, very simple phenomena. So, you have, it appears very trivial to you, but people working in this area have to now use this and build devices which doctors think it is some completely novel, because they do not have any understanding of fluid mechanics. Okay. And since all these have very good marketing potential, you go and build this device, patent it, you market it, and so that is how, because the medical applications are the most demanding applications, the most common, okay, where you can generate lot of revenue compared to the other industries. So, therefore, a simple bifurcation where you have one small diameter channel, the other is a large diameter channel. The small diameter channel will definitely pose resistance to platelets. So, therefore, the fluids will take path of least resistance, the platelets will run through the larger diameter one, okay. And then you have many of these such bifurcations, so that you increase the separation efficiency. At the end of this device you can separate the plasma from platelet. So, this is a very simple device, just path of least resistance and you alter the diameter of these channels, but it has such a very potential impact where the separation is a big problem. You have to go to a equipment which is very expensive at large scale and you have to do it. Now, if you have this microfluidic device, you do it within your palm, okay. So, that is how these get a lot of publicity in that sense. So, microfluidics has become very important topic in microscale flows, more important than, for example, microscale heat transfer, okay, because the number of applications dealing with biomedical medical applications are much more than with electronic cooling, right. And electronic cooling is kind of a saturating problem. So, there is always you cannot increase the processor speed beyond a certain point, because you are miniaturizing it already and you do not have too much of space to put very sophisticated cooling technology, right. So, even if you build a micro channel within the chip, okay, so the processor can only be this much fast, right. So, therefore, if you look at the average processor speeds in the last 4-5 years, they have not tremendously gone up. So, near about 3 gigahertz, right. Whereas, if you look at processor speeds in the last 15 years, you would see a big difference from megahertz. Now, we have gone to gigahertz, but now once it has approached 1.5, then 2, 3 gigahertz, now you do not see a marked improvement, okay, very marginal improvement in the clock speeds. So, that shows that thermal dissipation is a big problem and you cannot do much, because already you are shrinking the size of these devices. So, at the same time you cannot increase the clock speed. So, there is a kind of saturation in the electronic cooling area, okay. Whereas, if you look at biomedical applications, there is always scope for everything, okay. A better diagnostic device, better treatment device, okay, which is more comfortable, which is more compact, less intrusive, okay. So, all these keep on evolving, there is a lot of challenge, and most of the guys working in that area, they do not have any understanding of how to build these devices, okay. Let it be doctors or health professionals, they do not have any understanding of the fluid mechanics. So, that is how the microfluidics is gained a lot of popularity, okay, because of the tremendous applications in biology, okay. So, therefore, how do we achieve all these microfluidic functions? Pumping, mixing, separating, dispensing. So, these are phenomena which has been known for at least 100 years, but we have never emphasized this for the large diameter channels, okay, because at small diameter channels all these forces, surface forces now start appearing, and we now can make use of these forces to cause all these functions, okay. So, therefore, when you look at the different phenomena, so what I am going to emphasize here, you can talk about magnetokinetics also. You can talk about using body forces or other surface forces, capillary forces also to induce motions, okay. So, you can have thermocapillary motion, okay. You can have capillary induced motion, you can have magnetokinetics, but the most important fundamental and most commonly used feature is the electrokinetics, okay. So, therefore, if you look at the most important electrokinetic phenomena, I would say there are two of them. One is called the electroosmosis, the other is called electrophoresis. Okay. You can also have case where you have a movement and this can cause an change in the electric field, electric potential. So, those two come under what we call a streaming potential or sedimentation potential. So, you have two types. So, one, you induce a electric field, you apply an electric field externally and then you move the flow, you induce a flow. So, that is coming under electrophoresis or electroosmosis. And when you say electroosmosis, so this is where you have fixed plates or fixed body walls, so which are charged. The charges actually are accumulating at the walls and close to the walls, but the walls are fixed and what is moving is the fluid, bulk fluid. Okay. In the case of electrophoresis, you are talking about say particles or charged ions or metallic particles which have charge, and these can actually move relative to the fluid. So, you can have therefore two types of motion, one the motion of the bulk fluid, walls being fixed, and the force, the Coulomb force which is acting on this bulk fluid, it is due to the electrostatic charge potential at the walls. Okay, that is the electroosmosis process. So, the other process is the electrophoresis, where you can have charged bodies or charged particles in a stationary fluid, and these can be accelerated by means of external electric field, that is called electrophoresis. And if you do the reverse, so you can actually have a charged particle or charged metallic surface and you move them, that will induce an external electric field, that will induce an electric field. So, that is used in the case of streaming potential and sedimentation potential. So, those two we will not look at in this lecture, but we will emphasize only on the electroosmosis and electrophoresis part. So, just to say how what is the fundamental physics behind the electrokinetics in general. So, if you take any polar liquid, okay, so which has a net charge and you immerse an object in this or a boundary or a wall into this polar fluid, what happens is this particular wall at this right at the surface will acquire some charge being in contact with the polar fluid. So, for example, in this example it shows that the surface is now negatively charged. So, you have excess negative charge at the surface, and this is common, it need not be at small scales, it can be at any scales, but at large scales you do not find this is causing any difference if you do not consider this into account, but at small scales this becomes quite important. So, therefore, you have a charge, for example, could be a negative charge, and what happens now, the base fluid that you have again has positive and negative ions. For example, water, you take H plus OH minus. So, therefore, the tendency will be for all the positive ions to come and settle down towards the wall, right, because the wall is now negatively charged. So, therefore, the first layer of positive charge which is accumulated on the wall, this is called the Stern layer. Okay. So, STERN, Stern layer, and as you see that this is almost stuck to the wall. So, it cannot move. So, these are positively charged ions which are stuck to the negatively charged body. So, the interaction potential is very large. So, you cannot simply separate them. So, it looks almost that is stationary, but what happens is there is a net negative charge at the wall. This cannot be simply compensated by the Stern layer positive ions. So, still some more positive ions from the bulk keep diffusing towards the wall. So, therefore, if you look at lengths which are much larger than the first layer, which is the Stern layer, you see a diffusion of these positive ions closer and closer to the wall, and far away from the wall there is no net charge accumulation. Okay. Far away from the wall the fluid becomes neutral electrical, but close to the wall the charge accumulation will diffuse. Okay. So, therefore, there is another layer above the Stern layer called the diffuse layer, and outside the diffuse layer the fluid will become electrostatically neutral. Okay. So, if you therefore draw the potential, electrostatic potential right at the wall, this is where the Stern layer is the highest value of electrostatic potential, that is the gradient. This is related to the gradient in the concentration of the ions or positively charged ions in this case. Okay. And this is there till Stern layer, and then from the Stern layer you have a more gradual reduction in the potential, and finally this value becomes equal to the bulk value. Okay. So, asymptotically as you go to large distances from the wall, this potential goes to 0. Okay. So, therefore, the combination of the Stern layer and the diffuse layer together is called the electric double layer. So, when you really zoom with a microscope and you go to 1 ion distance from the wall, you find the Stern layer which is stationary. For all practical purpose there is no motion of the Stern layer, it is just there stuck, and above this you have the diffuse layer where you have a gradual reduction in the potential, electrostatic potential, and finally far away from the wall even this potential will decay, okay, and the fluid becomes neutral. So, now what is so important about this? That means there is a potential, that means if you apply an electric field, so these charges will now therefore move in the direction of the electric field. Okay. So, and this happens primarily at the diffuse layer, because that is where the thickest layer is, and that is where the maximum change in the potential happens. So, therefore, when you apply an external electric field, you find all the ions in the diffuse layer actually moving, okay, and therefore, this motion will appear as though that the wall is now fixed, but the diffuse layer is just moving. It is like a co-ed flow. Okay. So, the way to analyze this particular problem would be to therefore solve for the region where you have the diffuse and Stern layer, get the solution. At the edge of the diffuse layer, you know what will be the velocity, okay, and now treat this problem like a co-ed flow with a slip and apply the particular velocity as the slip boundary condition. So, the outer region will be a pure Navier-Stokes without any external forces, because the external forces cannot induce any motion in the outer external flow, because it is electrostatically neutral. Okay. So, only the diffuse layer will actually move, and to make this problem simple, we only solve the double layer separately with the Coulomb force, calculate the velocity at the edge of the double layer and give that as a slip boundary condition to the conventional Navier-Stokes equation. So, in the end what you have is a net motion of the fluid, okay, and that will be, if you take the simple case, if you have two plates, one on the top, one on the bottom. So, you just have a constant velocity between these two diffuse layers on the top and bottom, because that is the limiting case of the co-ed flow. The co-ed flow with both walls, top and bottom walls, moving with the same velocity, what will be the velocity profile? It will be the same as the wall velocities. Okay. It will take the average velocity between the top and bottom wall. If both the walls move at the same speed in the same direction, then the net bulk motion will also be same as u. If one wall moves in this direction, the other wall moves, then at the midpoint it will be 0 velocity, top half will be moving in this, bottom half will be moving. So, it is a linear profile. If one wall moves with u1, the other wall moves with u2, then the velocity profile will take average of them. Okay. So, therefore, in this case the simplest solution for co-ed flow will be whatever velocity you have at the edge of the EDL, so that velocity will be uniform throughout the bulk. Okay. So, therefore, to just give you some definitions, so we have the definition of delta, which is called the Stern layer thickness, right, and we have the thickness of the diffuse layer, which is given by lambda subscript d, and if you measure the potential difference between the bulk fluid and what is there at the edge of the Stern layer. So, this is the edge of the Stern layer, correct. So, you have a certain value phi, okay, phi at the edge of the Stern layer. For the bulk you have a certain potential phi bulk. So, that difference will give you what is called the zeta potential. Okay. So, therefore, at the wall this potential difference is phi w, okay, the actual potential at the wall and minus the bulk value, that is your phi w, and at the edge of the Stern layer this potential difference becomes what is called the zeta potential. So, these are some of the standard notations and definitions used for the electric double layer. Okay. So, now again this is another schematic, very enlarged magnified view of the electric double layer. So, what it shows is you have a silicon surface, silicon material, which actually possesses a negative charge, that is what is given by this O minus. So, now when you put an aqueous solution of potassium chloride, okay, so you can have some salts in your fluid, in your water, it need not be only pure water, you know. So, you can have some salts, it can be sodium chloride or potassium chloride or some other ions. Okay. Now, what happens is all the positively charged ions are now pulled close to the wall. So, you can see that there is a H plus ions and also K plus ions can also come and get stuck, and slowly from this there is a build up of the positively charged ions, which makes the diffuse layer, and far away above, much above the diffuse layer, again the net charge will be 0. So, you have more or less equal number of H plus and OH minus, K plus and Cl minus ions. So, you do not induce any electrostatic potential, but close to the wall you have the Stern layer right at the wall and you have the diffuse layer. So, what will be the, so we are not really bothered about calculating the Stern layer thickness, because that is really not going to affect anything, it is almost motionless. So, it is not going to appear anywhere. So, the most important layer will be the diffuse layer, and generally the diffuse layer can extend of the order of few tens of nanometers. Okay, it is again a nanometer scale phenomena. Okay. So, if you are drawing the potential distribution, the same potential distribution that we draw here, you have the wall potential at the wall and slowly gradually it drops to the bulk. So, therefore, if you take the potential difference between the bulk and the particular point, so that will be your potential difference, and that will be 0 at the bulk, and at the wall you have the maximum, right. So, yeah. So, therefore, if you consider this particular case, so we have an aqueous solution containing dissolved ionic species, each of this is denoted by I, it could be H plus or K plus, Cl minus, OH minus. So, each of these species is denoted by the index I, and each ion has a bulk concentration Ci, okay, and a valence or charge number Zi. So, just to tell you what these values are, if you for example have a 1 millimole solution of sodium chloride, okay, the bulk concentration of Na plus and Cl minus will be both same, okay, but the valence number will be different. This is Na plus and this is Cl minus. So, the valence number for the Na will be 1 plus 1 and Cl will be minus 1. Okay. So, therefore, we use the subscript bulk or infinity to define properties in the bulk far away from the wall. Now, why are we bothered about this bulk concentration and valence number? Okay. So, now we know the double layer potential is given at any point in the right from the wall to any region in the diffuse layer. It is the potential difference is nothing but the actual electrostatic potential at that particular location minus the bulk value. Okay. So, therefore, if you want to understand how to calculate the net charge density, okay, based on this particular potential, right. So, this net charge density is what is going to cause the motion if you place an electric field, external electric field. So, how do we calculate the net charge density? So, this net charge density is calculated for each species of the ion. Okay. So, you know what is the particular bulk concentration, okay, times what is the valence number, okay, times F. So, F is called the Faraday's constant. So, if you multiply them and sum them over all the species, so you get the net charge density. Okay. And the question is, how do we calculate Ci, because Ci is actually a local concentration. So, it has to be related to the bulk value Ci infinity. So, and how is it related? Through the Boltzmann statistics. So, we are using Boltzmann statistics again, okay, after we talk about nanoscale, now again in terms of concentration distribution. So, in the actual Boltzmann statistics for energy, we had in the numerator energy E divided by kBT, right. So, that is rewritten. So, that energy now is replaced by ZIF into phi corresponding to the charge, electrostatic potential. So, this gives you the distribution of your concentration from the wall to the bulk value at Ci infinity. So, therefore, if you say your phi equal to 0, so phi equal to 0 means this is at the bulk, phi is equal to phi minus phi bulk. So, when can phi be 0? Only if your electrostatic potential is same as your bulk value. So, in that case the value of Ci will be equal to, so there should be an exponential here, okay, there is a mistake, please correct it, there should be Ci infinity into exponential of that. So, when phi equal to 0, so your concentration equals the bulk concentration, and that bulk concentration is given by this, correct. And from there what happens to this concentration as your phi keeps increasing? As your phi becomes larger and larger, reduces. Okay. So, therefore, using this Boltzmann statistics we can now plug in into the expression to calculate the net charge density rho, correct, because the net charge density will give you at a particular level what is the concentration. Based on that concentration of ions you can calculate the charge density. So, in order to therefore know the concentration distribution, we use the Boltzmann statistic, substitute into this, and therefore, the net charge density can now be written as a function of the potential difference phi. Okay. So, expressed through the Boltzmann solution. And now, what do we do with this rho e? Now, this rho e is at a particular location, right. This is the net charge density at a particular location. So, we have expressed this in terms of the local electrostatic potential difference and as a function of the bulk concentration of the species. So, now based on this at a particular location you calculate what is the value of the net charge density, and once you know that you can write your Poisson's equation, okay, which states that your Laplacian of your electrostatic field, electrostatic potential is related to, is nothing but minus your rho e by epsilon. Okay. So, here epsilon should be the permittivity. So, therefore, you solve the Poisson distribution. So, this Poisson distribution function will so this particular equation links your potential to the local charge density, and therefore, we now plug in from the previous equation the expression for rho e into the Poisson equation, and this equation is now called Poisson-Boltzmann equation, because the original Poisson's equation has the local charge density, and through the Boltzmann distribution we are bringing in the relation with respect to the free stream concentration of a particular species. So, therefore, this particular equation is called the Poisson-Boltzmann equation. So, you can also non-dimensionalize this equation. So, we can call this as phi star, where phi star can be f phi by RT. This is some kind of non-dimensional electrostatic potential in terms of Faraday's constant R and T. And similarly, you can non-dimensionalize the length scales, okay, using the length d by length lambda d. So, this d by length is also referred to as the length of the diffuse layer, right. So, we have mentioned that the diffuse layer is given by the height lambda d. So, that is also sometimes called the d by length, and so we have already talked about mean free path. So, this is something similar to that. So, d by length gives a measure of the characteristic length over which the over potential at the wall decays to the bulk, very simple definition. So, the over potential is basically your phi minus phi bulk. So, from the wall, so it takes a distance of lambda d or the d by length to decay to the bulk value. So, the over potential should become 0 from the wall potential. So, this distance is given approximately by a empirical correlation from scaling arguments. Okay. So, you can use this particular expression to approximately calculate the order of magnitude of d by length, and most often it turns out to be of the order of 10 nanometers or so. Okay. So, therefore, the Poisson-Boltzmann equation, if you non-dimensionalize using a non-dimensional electrostatic potential and d by length, you write it in terms of non-dimensional numbers. So, we will stop here. Tomorrow we will see how we can solve the equation, because this equation right here, is it linear or non-linear. So, this is going to be a non-linear equation. because you have a function of phi in both the sides, left hand side and right hand side. So, in order to solve this, you have to guess the solution for phi, substitute it and see if it is satisfied and do this iterative process. So, therefore, to get a simple analytical solution, we try to linearize this equation and solve directly for phi. So, we will therefore convert the nonlinear Poisson-Boltzmann equation into a linear Poisson-Boltzmann and find the solution for phi. So, that we will continue tomorrow.